So we are going to do eigenvalues and eigenvectors today. And eigenvalues and eigenvectors represent an incredibly useful concept in linear algebra. And we can see their application not just in math, but also in physics, especially quantum physics. Eigenvalues can be used to solve systems of linear differential equations. So let's write that down maybe. So eigenvalues are used to solve systems of linear differential equations. Also, it is used to describe natural frequencies of vibrations, and then it's also used to separate nodes of motion and distinguish states of energy. And much more. So just what are eigenvalues exactly? Before I define eigenvalues and eigenvectors to you, let me tell you what does the word eigenvalue mean. So it comes from the German word Eigenwert, where Eigen means characteristic and the word word means value. So eigenvalue is also known as characteristic value. Now this will make more sense to you when we talk about how to find out eigenvalues by equating characteristic polynomials to zero to find out the roots of the equation. So now let's define eigenvalues. So the definition of eigenvalues and eigenvectors. So here, if a matrix A is a square matrix of size n by n, then a vector x which is not equal to 0 vector, or just, it's okay, let us write 0 vector, is an eigenvector of the matrix A if it fulfills the condition, that is A times the non-zero vector x is equal to a scalar multiple alpha times the non-zero vector x. So what I'm saying here is that a square matrix A has a eigenvector x if the eigenvector x is not zero, it's a non-zero vector, and it fulfills this condition here. All right. So here x is your eigenvector and lambda is your eigenvalue, which is also known as the characteristic value sometimes. So characteristic value. And also this is a scalar. So this is a scalar. Now the matrix A can have multiple eigenvalues, but not more than n, the number of rows or columns. So the matrix A is an n by n matrix, and the number of maximum eigenvalues that the matrix will have is n. And each eigenvalue will have its corresponding eigenvector. So maybe let me write that down. So uh, n by n matrix has n eigenvalues. Let's name them lambda 1, lambda 2 until lambda n. And corresponding to each eigenvalue, you will have an eigenvector. So that's the definition of eigenvalues and eigenvector. I hope it's clear to you. I'll just go through it one more time. So if you have a matrix A, which is a square n by n matrix, it has an eigenvector x if that is non-zero vector, and it fulfills the condition that if you multiply the eigenvector with the matrix, it will be equal to the eigenvector itself with another scalar multiple. And this scalar multiple is the eigenvalue and the x is your eigenvector. If you have any doubts, please let me know. And also we said that an n by n matrix will have n eigenvalues, and each of these eigenvalues will have a corresponding eigenvector. So each eigenvalue has its own eigenvector. That's all. That's the definition that I said over here. If you do not understand, please let me know. So now, how to find out eigenvalues and eigenvectors? Or let's just first only, let's say how to find out eigenvalues of square matrix. All right. So we know that if we want to find eigenvalue of a matrix A, then it has to satisfy this condition here, which is the matrix A when multiplied with the vector or eigenvector x is equal to a scalar multiple lambda times the eigenvector again. So this is how we can find out the eigenvalues of a square matrix. So what we do is that we take the lambda x to the other side of the equation and we can write it as matrix A times x minus lambda times vector x is equal to 0. And this is also a vector. So here we can introduce another vector with the lambda and the x between them, we can introduce an identity matrix, which is equal to 0. And then now if we take the x common out, so we take the x, or let's write it on the other side. So we'll have here A minus the lambda times the identity matrix times x, which is taken out as common, is equal to the 0 vector. So here, why did we put in an identity matrix? Okay, sorry about this here. Okay, so why did we put here an identity matrix I? It's because it doesn't make a difference, first of all. So even if you put an identity matrix I here, the end result of this is same. Next, if you multiply the identity matrix to the x, it is still x, there is no change. But then when you want to subtract the matrix A minus lambda I, if there is no identity matrix here, you cannot subtract, like you can only subtract a matrix from a matrix. So we have made this now a matrix by multiplying the identity to the lambda. But if this was not done, then we would have to subtract a matrix minus a scalar number, which is not possible. That's the reason why we put the identity matrix here. So now we want a non-zero solution to this equation here. So we want for this equation here a non-zero solution, which means that this vector here cannot be a 0. So this cannot be a 0 vector. So let's see what this means for alpha minus lambda I. So we know that if we want non-zero equation to this one, solution to this, and x cannot be a 0 vector, then a minus lambda I cannot be invertible. Let's say it is invertible. So let's say that this matrix here, so let me take a different color here. So this matrix here is invertible. So if this is invertible, in that case we can multiply the inverse of this matrix to both sides. So we'll get here A minus alpha I inverse times the matrix A minus, sorry, not alpha, but lambda I times x. So this one here is my workout to say that if this matrix was invertible, so let me write that in case you don't get confused later. So if this matrix was invertible, that means it has an inverse. In that case, this would be the situation here. Then we can multiply the inverse of this matrix here on both the sides. So we'll have here A minus alpha times the identity matrix inverse times 0 vector. So this one here is equal to 1. So we will have here then x is equal to A minus the lambda times the identity matrix inverse times the 0 vector. And as you can see, this is equal to 0. So we have x is equal to 0 vector in that case. But then we don't want x to be a 0 vector, right? So for that, this matrix here is not invertible, means it does not have a inverse. And if it does not have an inverse, that means A, or let me change the color. That would mean that A minus alpha I is not having an inverse, and it is therefore singular, and therefore the determinant of this matrix here is equal to 0. So again, how to find out eigenvalues of a square matrix? We took our condition here that we need to fulfill to find out eigenvalues and eigenvectors, and then we did some swaps. And then we are saying that the x cannot be 0, and this matrix here, A minus lambda I, is not invertible. Then I have proved it to you why it is not invertible. Because if it is invertible, then we get x to be equal to 0, which is not what we want here. So this one here is not invertible, and if it is not invertible, which means it does not have an inverse, which means it is singular, therefore the determinant of this matrix will be equal to 0. And this one here is your characteristic equation. Okay, and expanding this characteristic equation will give or will form a polynomial referred to as the characteristic polynomial of degree n. So that will look something like this one here, which is lambda to the power n plus constant c1 times lambda to the power n minus 1, and then we'll have here c2 times lambda to the power n minus 2, plus we'll have constant n equal to 0. So since we have an nth order polynomial here, which we are equating it to 0, we will get n roots for this polynomial, and those n roots will be the eigenvalues of the matrix A. Okay, up until here, is everything clear to all of you? Please let me know. Okay, great. Great. Happy to hear that you all understood, because I don't want you all to be lost in between. Okay, then now let's do an example to get more clear what we are talking about here. Okay, so this is our example 1, let's say. Find eigenvalues and eigenvectors of a given matrix A, which is 1, 1, 4, 1. Now, to find out the eigenvalues and eigenvectors, what we use is the characteristic equation. The characteristic equation is determinant of A minus the matrix A minus lambda times the identity matrix is equal to 0. So that's the characteristic equation, and that's what we'll use to find out eigenvalues and eigenvectors. Now let's solve this separately here. So we have A minus lambda times the identity matrix. So A we know is 1, 1, 4, 1, and minus, if you multiply the lambda to the identity matrix, you will get here lambda 0 0 lambda. Okay, so as you can see, what will happen here is that the lambda will be subtracted from the diagonal elements here. Okay, so we have 1 minus lambda, 4 minus 0 is 4, and 1 minus 0 is 1 again, and then again we have 1 minus lambda. Now we'll find out the determinant of a minus lambda times I. So sometimes I might not give these square brackets around because it's not very necessary. So it's just to show you that these are matrices, but even if I don't give, it's fine. It's even you can write it as like that, it's fine. So here, to find out the determinant of this particular matrix here, you know that we have to multiply the opposite sides here. So we have to, let me write it down. So determinant of the matrix 1 minus lambda 4 1 1 minus lambda. So we will multiply these two elements here. So 1 minus lambda times 1 minus lambda minus these two elements here. So that will be 4 times 1. So now we know that we have to equate this to 0, or let's finish writing or solving it. So here we'll get, if you FOIL it out, you will get 1 minus 2 times lambda minus lambda squared minus 4. So this one here is equal to lambda squared minus 2 times lambda minus 3. And as you know, the characteristic equation here says that the determinant of the matrix A minus lambda times I is equal to 0. So we take the characteristic polynomial that we got here and we equate it to 0. So we'll equate lambda square minus 2 lambda minus 3 to 0. Okay, now you can see this is a quadratic equation here, so you can solve it using the quadratic formula. I hope all of you know how we get I. Okay, fine. You got confused there. No problem. I'll rewrite it. So here, I'll rewrite this step. So here we have the A minus lambda times identity matrices. Yes. Someone wants to say me something? I'm not understanding what are you saying, Majid. 1 comma minus 3. What do you mean by that? And Noor, if I'm answering you right, please let me know, okay? What I'm assuming is that you're confused from what happened to the identity matrix, or I don't know, here in this page. If not, if you have doubt in the previous page, let me know that. So here now we have lambda times the identity matrix, which is 1 0 0 1, and that is, if you solve that here, you will have, again, let me write 1 1 4 1 minus, when you multiply the lambda inside here, you will get lambda 0 0 lambda, and that gives you, I don't want to write it down there then anymore because I wrote it here, so that gives you this answer here. The roots are 1 and 3. Okay, yeah, okay, great. Noor, could I answer your question? Yes, okay, fine. So here now, If you use the quadratic equation, let's do that. So
Miss,
yes,
in the last equation you wrote lambda square minus 2 lambda, but lambda square is minus.
here you mean. Okay, I made a mistake. It should be plus. Thank you. It should be plus. So 1 minus 2 lambda plus lambda square minus 4. Okay, thank you for that. Now, if we go ahead and try to solve this using the quadratic equation, let's say we have two values of lambda for the quadratic equation. So we have here minus b. So I hope you all know the formula. So you have minus b, or b value is minus 2, plus minus square root of b squared. So we have minus 2 squared minus 4 times a, which is 1, times c, which is minus 3, divided by 2 times a, which is 1. So this gives us 2 plus minus square root of 16 divided by 2. Then we get here 2 plus minus 4, 2. So you can say lambda 1 is 2 plus 4 divided by 2, which is 3. And lambda 2 is 2 minus 4 divided by 2, which is minus 1. So we got two lambda values of us. So we can say that the eigenvalues are lambda is equal to 3 and lambda equal to minus 1. Okay, any more doubts?
Miss, it's able to use calculator to find the roots instead of the formula.
If you can use it, you can use it. There is no problem. I don't have any problem if you give me the answers through calculator.
Okay, thank you.
Of course, there is a way to use. If you're asking, is there a way? Yes, there are some calculators which can solve quadratic equations directly. Okay, so now we can solve for the eigenvectors, but know that for each eigenvalue here, we have a different eigenvector. So for each one, we have to find out the eigenvector separately. Now, again, for finding out the eigenvectors, um, we have to use the characteristic equation, which is a minus lambda I times vector x. So I'm really sorry if I present it in two different ways sometimes, because both are correct. So I can write it here as this one here, which represents that this is a matrix or this is a vector, but I love to represent it the other way too. So yeah, so this is equal to 0. All right, so this is the characteristic equation. And now here we know that we have the value for lambda, and the eigenvector is something that we don't know. It's unknown to us, and we are trying to search that now. So this one, if you try to solve now, we will end up with a system of equations to solve. But there is something to be noticed here. That is, we will sometimes here have to choose values for the components of the eigenvectors. Let me write that down. We will sometimes have to choose values. Choose values for the components of the eigenvectors. Okay, so while searching eigenvectors, sometimes you have to choose some values for some of the components. Now, this doesn't really matter or affect because the solution we find by doing this only represents the form of the eigenvector. So it's the eigenvector that we'll get by choosing values is a form of the eigenvector for that eigenvalue. So there could be multiple eigenvectors for that particular eigenvalue. What I'm saying will get more clearer with time. So the solution of this equation gives only a form of the eigenvector, and any scalar multiple of the answer is also an eigenvector. So let me explain that to you in a bit more detail. So here we know that the condition for eigenvectors is that A times x is equal to lambda times x, right? So now if we have here A times, or it's too confusing if I write it this way, but you can understand it more clearer if I say that A times vector x is equal to lambda times vector x. Okay, so now if I replace, or if I say that the vector x is actually a constant times the vector x, so this means here if I take out the c is a scalar multiple of the x, so if we take it out we'll have here c times a times x vector, and this one here we know from the above equation we know that ax here is equal to lambda x, right? So we can replace this by c times lambda x vector, and here now if you take out the lambda you will get here lambda is c times the x vector. So by definition you can say that a of of x vector with multiplied to a scalar constant will be equal to lambda times c times x vector. So here what I mean is that this is also an eigenvector by definition. So if you multiply a constant to the eigenvector and it still fulfills this condition here, then that constant multiplied to the eigenvector is also an eigenvector. Okay, you will understand this in more detail when we start solving now for the eigenvector. So let's remember or recall back, our matrix was 1 1 4 1, or maybe let me just write it down here so that let's just write it down as an example 2 maybe, where we are finding, oh no, I wrote it at first, that we are finding, so you can say continuation of the example 1. So from here on we are continuing, we are finding out the eigenvector now. So the matrix A is 1 4 1 1, and we know our lambda values are 3 and -1, and to find out the eigenvector we have to follow the characteristic equation, which is a minus lambda I times vector x is equal to the 0 vector. Now let's solve this one first here. So a minus lambda times the identity matrix. And we will replace for the lambda here as we have the value. So we will replace it with our value now, which is 3. So we are going for finding out the eigenvector for 3. So this one here will be A is 1, 1, 4, 1 minus 3 times the identity matrix will be 3, 0, 0, 3. So I hope you're not confused again. The identity matrix is 1, 0, 0, 1, and if I multiply the 3 inside that, I'll get 3, 0, 0, 3, right? So if you subtract them, you will see that we are subtracting the 3 from the diagonal elements here. So 1 minus 3 is minus 2, and then 4 minus 0 is 4, 1 minus 0 is 1, and 1 minus 3 is minus 2. Now we have to find out the determinant, or no. So we have to multiply this one here now to x, which is an unknown vector. So let's say x vector is equal to x1 and x2. Okay, be the eigenvector, be the eigenvector corresponding to lambda is equal to 3. So then now using the characteristic equation, we will have here, maybe I'll not write it on this page here, but on the other page, so it's easier to see. So we have A minus lambda I times x vector is equal to the 0 vector. So A minus lambda I we just solved here and we got this matrix. This matrix here is A minus lambda I. So we'll copy and put it here. And we told that x is x1 and x2, the unknown vector, which is equal to 0, 0. So as I told you, we'll get a set of equations here now to be solved, but then we can choose values for the components of the x vector. So let's say, or let's choose x1 is equal to 1. In that case, now we'll have the equation, the first equation will be minus 2 times x1 plus 1 times x2 is equal to 0. So we chose x1 to be 1, so we'll have minus 2 times 1 plus 1 times x2 is equal to 0. So we'll have here x2, the minus 2 will go that side and become 2 here, and then we'll have divided it by 1, which is equal to 2 again, so I'll just not write the division by 1. So x2 is 2. So we got our values now, x1 as 1 and x2 is 2. So the x vector we can say is equal to 1, 2. Now, as I told you before, that this is just a form of eigenvectors, the form that eigenvectors takes for this eigenvalue. So to put it simply, any vector where the second element, so let's say any vector where the second element is a multiplication or is a is twice the first element, is an eigenvector for the lambda is equal to 3. Okay, so this here is the eigenvector for lambda is equal to 3. It's a form, so it's not like You can multiply any scalar quantity to this vector here, and still it will be an eigenvector for lambda is equal to 3. That's what I mean. Okay? If anything unclear, let me know now.
Yes, miss. Why did you choose x equal to 1?
Okay. As I told you before, here we will we will sometimes have to choose values for the components of the eigenvectors, right? So that is the reason we chose here x1 to be equal to 1 here, and then we get x2, and what we are saying is that we are trying to find here a form of the eigenvector. Not like eigenvectors are, as I told you, if you multiply any constant to this eigenvector here, it will still be an eigenvector for lambda is equal to 3. So eigenvectors for lambda is equal to 3 is whenever we have the first element and as the element itself, and then the second element will be a multiplication by 2 of the first element. I hope I could answer you. Can we take any number for x1? Usually it's good to take 1, but if you want you can take some other numbers, yeah, no problem. But again, if you take it out as the constant, if you take out the scalar multiple, you will come back to 1. Okay, so now let's do the same thing for lambda is equal to, let's find out the eigenvector for lambda is equal to -1 now. So again, we'll take our equation, which is a minus lambda I times vector x is equal to 0 vector. So we have a is 1, 1, 4, 1, minus lambda is now for us -1. So if we put in the identity matrix, we'll have here -1, 0. We assume any value for it. Okay. So we have -1, 0, 0, -1. And this here is equal to or should I do it at once? Okay, let me write it at once here. So this one here times the vector x is x1, x2 is equal to 0, 0. So now here you will get 2, 1, 4, 2 times x1 times x2 is equal to 0, 0. Okay, now again, let's choose for x1 is equal to 1. And if we do that, or maybe because you all had a confusion, right? So why we're choosing 1 here? Let's not choose 1 and let's show that I'm just choosing any constant c here for x1 now. Okay, so now if I choose any constant c here, what will I get? I'll get here the equation 2 times x1 plus 1 times x2 is equal to 0. So we know that x1 is c, so 2 times c plus x2 is equal to 0. Now x2 is equal to minus 2c. Okay, so we took x1 as any constant c and we took x2 as minus 2c. So the eigenvector for us is c comma minus 2c. Now if we take out and scalar multiple out of it, so you can just say we take out the c here and we'll get here 1 comma minus 2. So which means that if you multiply any constant to this vector here 1 comma minus 2, it is still an eigenvector of lambda is equal to 1. So you can say that the eigenvector for lambda is equal to 1 is 1 comma minus 2, or any multiple of it. For example, let's say 2 times 2 is 2, 2 times minus 2 is minus 4, so 2 and minus 4 is also an eigenvector for lambda is equal to minus 1. So I hope I could answer your question now, and you all understood up till here everything. Is it clear? Okay, okay, great, fine. So now let's go ahead and try to solve a 3 by 3 matrix. So let's go for an example 2. Here and find eigenvalues and eigenvector for the given matrix A, which is equal to 1 0 0, 3 minus 2 0, and 2 3 4. So to find out now the eigenvalue, we have to do we have to solve the characteristic equation, which is determinant of a minus lambda I is equal to 0. So let's first solve a minus lambda I. So we have here a is 1 0 0, 3 minus 2 0, 2 3 4, minus lambda times the identity matrix, which is 1 0 0, 0 0, sorry, 0 1 0 and 0 0 1. So if you multiply the lambda inside the identity matrix here, you will get, instead of all of these ones, you will get the lambda, right? So if I just multiply it in here, I'll get in all of these places lambda. So now we can see that we'll only subtract the lambdas from the diagonal elements. It's only in the diagonal. So we take the diagonal elements here and we subtract the lambda from these elements here. So we'll have 1 minus lambda, and then we have 3, 2, and here we have 0. Then we have minus 2 minus lambda, and then we have 3 here, 0, 0, and 4 minus lambda. Okay, now we have to find out the determinant of a minus lambda I. So the determinant of this matrix here. Now I hope you all know how to find out the determinant of a 3 by 3 matrix. First is we'll choose our row. So let's choose our row that we are going to multiply here as this one here. So we'll take the first element as 1 minus lambda, and we will multiply it to the, leaving the row and the column of this element here. We'll take a determinant of the other matrix that is left out. So the determinant of this matrix here is minus 2 minus lambda times 4 minus lambda minus 3 times 0. Okay, and then the first number here is positive, the next one will be negative. So we take the next element as 0 here. So let's write it in different color. The next element is 0. So 0 times anything will be 0, but I'll just write it here so you know. So leaving its row and its column, we will take the other two sides and we will find out the determinant of that. So it will be 3 times 4 minus lambda minus 2 times 0. Okay, now we will take this element here and leaving its row and its column, we will take the matrix here and find out the determinant. And also please get know the signs. So here first we'll have positive, then negative, and again positive. So it continues, then negative, then positive, depends on how big is your matrix. So here we have again 0 times, now we have here 3 times 3 minus 2 times minus 2 minus lambda. Okay, now we have here 1 minus lambda to be multiplied to, or if you multiply it, you have here minus 2 minus lambda and 4 minus lambda. This one here is 0, so we don't need to write it down because 1 minus lambda times 0 will be 0. And then we have here minus 0. This one here is also multiplied by 0, so everything is 0. And then we have plus 0 because everything there is also multiplied by 0, so we only have 0. Now we have to solve, or you can say expand this ones here to get our polynomial, and we'll get a cubic polynomial. But then as you can see over here, we already have the factorized values here. The cubic polynomial is already, we have it as its factors here. So we don't need to do that because we'll again come back to these factors here itself. So we can just use them directly to get our solutions. So here if we equate this to 0, the polynomial, so we have here 1 minus lambda times minus 2 minus lambda times 4 minus lambda is equal to 0. We get lambda is equal to 1 for the first, and then we have lambda is equal to minus 2, and then we have lambda is equal to 4. So these are the 4 roots of this equation, or the 4 eigenvalues. And now we have to find out the eigenvectors related to each one of these separately. So first let's go ahead and find out the eigenvector for our eigenvector related to eigenvalue 1. So how do we find that? We take our equation, that is a minus lambda I times x vector is equal to 0 vector. So we will first solve here a minus lambda I, and since we know the value of the lambda, it will be a minus lambda is 1 times I. So as you can see over here, we will have here just a minus the identity matrix. So again, a is 1 0 0, 3 minus 2 0 2 3 4 minus the identity matrix. So we have 1 0 0 0 1 0 0 0 1. and that will give us the matrix 0, 0, 0, 3, minus 3, 0, and 2, 3, 3. Now if you write it in this form here, we'll have A minus lambda I matrix, which is 0, 0, 0, 3 minus 3, 0, and 3, 3, 3. So this is what we just calculated, times the unknown vector x is x1, x2, and x3, because this is a 3 by 3 matrix. And then the 0 vector is 0, 0, 0. So now again we come to the part where we choose values for x. So let's say, let's choose x1 is equal to 0. Sorry, not 0, 1. Then for the first one we have all zeros, so there's no equation there. For the next one we have 3x1 minus 3x2 is equal to 0. And we know the value of x1 is 1, so if we replace that, we'll get here x2 is minus 3 divided by minus 3, which is equal to 1. So x2 is equal to 1. And then if we now look at the third equation here, okay, I wrote a value wrong here. This is supposed to be 2. We'll have here 2 times x1 plus 3 times x2 plus 3 times x3 is equal to 0. So now if we replace the values for x1, we have 1. For x2, we just got here 1 again. And x3 is what we're finding now. So you will get here x3 is equal to minus 5 over 3. Okay, so x, the eigenvector here is 1, 1, minus 5 over 3. Any doubts until here? Okay, okay, great. Okay, great. So then now we'll find out the eigenvector for the eigenvalue, the next eigenvalue, which is minus 2. So let's find out the eigenvector related to eigenvalue minus 2. And again, we will have to solve a minus lambda I times x is equal to 0. So first, again, solving for a minus lambda I. So the lambda is minus 2 for us now. So we have a minus minus 2 times I, which is, we have a is 1, 3, 2, 0, minus 2, 3, and 0, 0, 4, minus, okay, so here we'll have minus 2 times 1 is minus 2, 0, 0, 0, minus 2, 0, 0, 0, minus 2. So this one here will give us 1 minus minus 2 is 3. And then we have 0 minus 0 is 0, 0 minus 0 is 0. And here we have 3 minus 0 is 3, and then 0, 0. So minus 2 plus 2 is 0. And here we have 2, 3, and 6. Now once we got this one here, if we replace it in our equation, we'll have A minus lambda I matrix, which is this matrix here, times the unknown matrix x1, x2, x3 is equal to the 0 vector 0, 0, 0. So for the first one, we have here 3 times x1 is equal to 0. So x1 is equal to 0. The next one is same again. We have 3 times x1 is equal to 0. So x1 is equal to 0. So that leads to the same thing. And then we have 2 times x1 plus 3 times x2 plus 6 times x3 is equal to 0. So replacing x1 by 0, we'll have this thing, the whole 2 times x1 is equal to 0. So we can just delete that. And we'll have here 3 times x2 plus 6 times x3 is equal to 0. So x2 can be written in terms of x3, which will be minus 6x3 divided by 3. So that is equal to minus 2x3 here. So now let's say, let's choose x3 to be equal to 1. In that case, x2, if you put here 1, it will be minus 2. So our eigenvector is equal to 0 for x1, x2 is minus 2, and x3 is, we said, let's suppose it's 1. So that's the eigenvector for the eigenvalue minus 2. And then we will work for the eigenvector for lambda is equal to 4 now. So again, we'll solve A minus lambda I times x vector is equal to the 0 vector, and solving this part here, we have A minus the lambda is 4 this time times the identity matrix. So we have A is 1, 3, 2, 0, minus 2, 3, and 0, 0, 4 minus 4 times the identity matrix, which is 4, 0, 0, 0, 4, 0, and 0, 0, 4 is equal to, we have here minus 3, 0, 0, and 3 minus 6, 0, 2, 3, 0. Okay, so we have found out this part here now, A minus lambda I, and we will multiply the matrix that we just got here times the unknown vector x. So x1, x2, and x3, which will be equal to 0, 0, 0. Okay, now we have minus 3 times x1 is equal to 0, which means that x1 is equal to 0 for the first equation here. For the next equation, we have 3 times x1 minus 6 times x2 is equal to 0. So replacing x1 by 0, this whole term becomes 0. So we have minus 6x2 is equal to 0, which also says that x2 is again also equal to 0 here. Okay, now for the third equation we have 2 times x, or let me write it here. So 2 times x1 plus 3 times x2 plus 0 times x3, so that's 0, so we don't need to write that here. So this is equal to 0, and we know x1 and x2 are both zeros. So you have 2 times 0 plus 3 times 0 is equal to 0, so 0 is equal to 0. So we have no information about x3, as you can see over here. There is no information about x3. This makes x3 a free variable. So we can just choose a value for x3. So let's say x3, or let's choose x3 to be equal to 1. So in that case now, the eigenvector here will be x1 is equal to 0, x2 is equal to 0, and x3 is equal to 1. Okay, I hope until now everything is clear for everyone. Okay, great. Okay, so now we will look at the theorems for the eigenvalues and eigenvectors. So we will look for the theorems of eigenvalues and eigenvectors. Okay, forgive my handwriting because I'm writing a bit fast. And so let's talk about theorem 1 now. Theorem 1. So if you have a matrix A and it is a n by n matrix or n by n square matrix, and the matrix is either in upper triangular form or in lower triangular form, or diagonal matrix, in that case you can say then the eigenvalues of the matrix A are the diagonal entries of A, or of the matrix A. So again, if you have a matrix which is n by n square matrix and it is in the form either upper triangular matrix form or lower triangular matrix form or diagonal matrix form, then the eigenvalues of this matrix are the diagonal entries of A. Maybe I'll show you with an example. So let's look at an example for this. What are the eigenvalues of this matrix given here, which is 6, 0 0 0 7 3 0 0 9 5 7.5 0 and 2 6 0 minus 7.2. Okay, so focusing on the theorem that I just gave you all, can you all tell me what are the eigenvalues of this matrix here? Or first of all, tell me what kind of matrix is this? Upper triangular, lower triangular, or diagonal matrix? Lower triangular, yes, that's correct. So this here is a lower triangular matrix. Now give me the eigenvalues of this matrix. Yes, that's correct. Some some of you wrote it's upper triangular matrix. No, it's not upper triangular matrix because in the lower triangular area there are elements. In the upper triangular area everything is zero. So everything above is zero. So in that case this is a lower triangular matrix, not an upper triangular matrix. Okay, so moment says the eigenvalues are 6, 3, 7.5 and minus 7.2. Correct, moment. So because this is a lower triangular matrix that we just saw in the theorem 1, therefore you can say that the eigenvalues are, so let's say lambda 1 is 6 here, so eigenvalues are all the elements in this diagonal here. So just removing this part here. So all the elements in the diagonal are your eigenvalues. Okay, so lambda 1 is 6, lambda 2 is 3, lambda 4 is 7.5, and lambda, okay, made a mistake. So lambda 3 is 7.5, lambda 4 is minus 7.2. Great. Okay, so I hope you all understood the theorem 1. Simple. Now let's go for theorem 2. So theorem 2 says if, okay, so if your lambda or eigenvalue is equal to 0, and this is an eigenvalue, so basically lambda is equal to 0 is an eigenvalue of a matrix A, then the matrix A is a singular or non-invertible matrix, is a singular or non-invertible. Non-invertible meaning does not have an inverse. So it's a non-invertible matrix. So if lambda is equal to 0 is an eigenvalue of A, then A is a singular or non-invertible matrix. So I don't want to show an example on this because I hope you all understood this. So what I'm trying to tell you is that if there is a matrix A and it does not have an inverse, which means it is singular, which means the determinant of this matrix is equal to 0. In that case, the one of its eigenvalues is equal to 0. So, or the other way around, if one of its eigenvalues is equal to 0, then it is a matrix that does not have an inverse. Okay, Now, let's look at another theorem. Theorem 3. So, if matrix A is a n by n matrix, then the transpose of that matrix have the same eigenvalues as the matrix. So if we have a matrix A and it is a square n by n matrix, then the transpose of this matrix have the same eigenvalues as the matrix A. So for an example, for this one here, we can show an example. So let's say I have a matrix A, which looks like this one here, which is 2, 3.5, and 8, and minus 3.5, 5, and 1. And here we have 6 to 8.5. So the values, the eigenvalues of this one here. So given the eigenvalues of the matrix A, which are, let's say, lambda 1 is equal to minus 1.547, lambda 2 is equal to 12.33, and lambda 3 is equal to 4.711. And what are the eigenvalues of the matrix B, which is 2, 3.5, 8, minus 3.5, 5, 1, 6 to 8.5. Okay, can you give me the eigenvalues for the matrix B? So I've given you a matrix A and I've given you the eigenvalues of that matrix, and I'm asking you what are the eigenvalues for matrix B. Could you tell me the eigenvalues for matrix B? 2, 5, 8.5. Wrong. Look into the theorem. This is an example for theorem 3. Okay. Yes, Majid, the same. Correct, Momin and Ryan. So the theorem 3 is saying, so what you can see here is that B is actually nothing but A inverse. Sorry, A transpose, right? So every row here is a column here. Every row here is a column here. And the row here is a column here. So B is nothing but A transpose. And if given such a question in the exam, you should be able to notice that B is nothing but A transpose, and so the eigenvalues for B also will be the same as the eigenvalues for A. So the eigenvalues for B also will be minus 1.547, and lambda 2 will be 12.33, and lambda 3 will be 4.711. Okay, now we have theorem 4. So theorem 4 is eigenvalues of symmetric matrices are real. So if you have symmetric matrices, the eigenvalues of them are real. And what do I mean by symmetric matrices is that the matrix A is equal to its own transpose. So if you have symmetric matrices, the eigenvalues of this kind of matrices will always be real numbers. Okay, so then I hope you understood that one. Then let's go to the next theorem. Theorem 5. And that is eigenvectors of a symmetric matrix are orthogonal. But only for distinct eigenvalues. Okay, so what does this mean here is that eigenvectors of a symmetric matrix are going to be perpendicular to each other, which means they're orthogonal, meaning that if you multiply the dot product of these eigenvectors, if you try to find out the dot product of these eigenvectors of the symmetric matrices, they will be equal to 0, which means they're orthogonal. So if you find out the dot product of these eigenvectors here, so if you find out the dot product of these eigenvectors of a symmetric matrix, it will be equal to 0 vector. So, and that means that they are orthogonal, they are perpendicular to each other. But then there is a condition for this, that this only is true if or for distinct eigenvalues. So the eigenvalues needs to be distinct from each other. Only then this theorem is true. Okay, now let's work with, or let's go ahead and see what is theorem 6. So now we have theorem 6 here, which is if lambda 1 to lambda n are eigenvalues of a n by n matrix, of n by n or n by n A matrix, then the determinant of the matrix is equal to the absolute value of the multiplication of all the lambda values, which can be also written as absolute of product from I is equal to 1 till n of all the lambda i's. So again, if you have eigenvalues from lambda 1 till lambda n for a square matrix, which is of size m times n, then the determinant of this matrix here is multiplication of all of its lambda values. So this is also connected to, you can say, theorem 2. So here in theorem 2, we told that if lambda is equal to 0, then A is singular, right? Which means that determinant of A is equal to 0. So we can see that here, that if any of these lambda was actually a 0, then the determinant of A would be equal to 0, right? So if any of these lambdas here were supposed to be a 0, and 0 multiplied by other lambdas will become a 0, so the determinant is equal to 0. Okay, that's, I'm not sure if I prepared an example for this one here. So this is theorem 6. Yes, there is an example for this. So let's work out the example. So given the eigenvalues of the matrix A, which is 2, 3.5, 8, and minus 3.5, 5, 1, 6, 2, 8.5, are lambda 1 is equal to minus 1.547, lambda 2 is 12.33, and lambda 3 is 4.711. Calculate the magnitude of the determinant of the matrix. So calculate the determinant of this matrix and give me the answer, everyone. What would be the determinant or the magnitude of the determinant of this matrix? Okay, we have 89.88 or 89.86. Yeah, that's correct answers. Okay, correct. So here we have absolute of 1.547 times absolute of 12.33 times absolute of 4.711, which will give you 89 point, I don't know, all of you are saying 86, but I got 88. So I'm not sure. If I'm wrong, then I'll just take your values. So you have 89.86. So let me write that answer here. Okay. So I prepared more for today, but then I'm scared I will not be able to finish if I start the rest of the part here. So no, I'm sure I'll not be able to finish the rest of it if I start now. So then let me know if you all have any doubts up till now, and then we'll start the quiz if you do not have any doubts. Are there more theorems? No, theorems are done. Now I was supposed to show you how we are supposed to calculate eigenvalues and eigenvectors numerically, which means approximately. Till now we saw how to calculate it exactly. So we will do that maybe in the next class because we don't have enough time for that because that's a really long one and will take at least 30 minutes more. So any doubts still here? Okay. Okay, great. So if you do not have any doubts still here, then I will start the quiz. Maybe give me 2 minutes. So at 2:40, the quiz will start, and we'll finish it by 2:50. But you will have only 6 minutes to attend. So as you after you open the quiz, you have only 6 minutes to do it. Okay, but it will be open for a total of 10 minutes for all of you to attend. Okay. I'm here with you still on the meeting. So if you have anything you want to ask me or something, I'm still here. Or if you have any problem issues you're facing,